Hmm. All right. That was rough. Okay. Can you hear me?
Hey, yeah, I'm here. What am I looking at? I don't know. Everything's broken. It's fine. Hey, cool.
We are live now. So, all right. I just posted the link to the other one. And so, yeah, sorry about that. So we couldn't get into that channel. And so we're moving to this channel. But I'll periodically check back over here and make sure that people are redirecting here. But since we're live, I guess we could just get started pretty soon. So, hey, everybody, I'm Cody. I work at, I've been doing Bitcoin dev for a while and various Bitcoin projects, not nearly as much as Nifty. Lisa runs Base 58, and she's been working as a Core Lightning Core contributor for like a long time, and like basically knows everything about Bitcoin and Lightning. And so we did a Bitcoin curriculum a little while ago for Replit, and today we're going to go over some fun Bitcoin stuff. So Nifty, you want to do any more introductions while I set up
Yeah.
the link?
Hey, everyone. Working with Cody for about a year now, and we're excited to walk through the white paper with you guys. I run Base 58, like Cody was saying. We do in-person classes in Austin. We've got one coming up in 2 weeks, so check that out if you want to learn more about how Bitcoin transactions work in person. We'll also have one in March. I mean, in April, the last week of the month, we're doing a big conference in Austin called Bitcoin Plus Plus. So come check it out. But without much further ado, I think I might have to move downstairs because there's a construction. Cody set up this awesome replit that we're gonna go through. I think the plan, and Cody, correct me if I'm wrong, is to walk through the white paper that Satoshi wrote, and just see if we can like implement stuff from the white paper.
Yeah. Yeah, that's the idea. And so for anybody who's not used Bitcoin with Replit before, it's super easy because Replit has this Nix backend. You can see my screen, right, Nancy? I think so.
Yeah, it looks good. Yeah.
Cool. So if we go over here, you can go to any REPL and then show the hidden files. And if you open up the replit.nix, then over here in this Nix configuration, it'll just like specify the dependencies, and you can just add packages.bitcoin to any REPL that you're using. And if you do that, it's going to add all of the command line tools and install Bitcoin Core through Nix in your REPL, right? And so then you can do stuff like this, where you open a shell and you can start up a Bitcoin node. And so when you do that, we'll kind of be walking through the white paper and like some of the like what's happening behind the scenes for this, but it's going to look something like this, right? So this is going to start a node from my REPL, which will connect to a bunch of other nodes, and it'll start speaking Bitcoin to these other nodes. And as it's doing that, we'll kind of walk through that stuff, right? But just for example, there we go. I just started up this Bitcoin node, and so it goes in, it syncs the block headers, and then it starts checking the history of the blockchain. But let's kind of back over to the tutorial, and you can have this running on the side while we do this. So, gotcha. So, Bitcoin, a peer-to-peer electronic cash system, right? So Bitcoin is the first cryptocurrency, right? Well, it's a decentralized currency that Satoshi invented, right? And so from the abstract over here, I'll just read this one because this one's worth reading in full, and then we'll kind of jump around for as we're doing this, right? So Bitcoin, abstract. A purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. Digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. We've proposed a solution to the double spending problem using a peer-to-peer network. The network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. And this is going to be what I think Lisa and I spend the most time on, of doing this proof of work stuff, because this, I think, is what makes Bitcoin the most fun and interesting. And it's like also the most fun to implement. So the longest chain not only serves as proof of the sequence of events witnessed, but proof that it came from the largest pool of CPU power. As long as a majority of CPU power is controlled by nodes that are not cooperating to attack the network, they'll generate the longest chain and outspace attackers. The network itself requires minimal structure. Messages are broadcast on a best effort basis, and nodes can leave and rejoin the network at will. Accepting the longest proof of work chain is proof of what happened while they were gone. So there's a lot there. And if you guys have questions, like, feel free to put them in the live chat, and I'll occasionally go back and forth with that. Right. But like for me, the thing that I always take away from what makes Bitcoin special and what makes it cool is that because it's using proof of work and because it's doing this hash chaining thing, is basically what Satoshi like to say is that the proof of work speaks for itself. Like, there's no way to falsify this stuff. It's not like I have to trust somebody. But if I can get access to the information, I can verify the information for myself. So I don't know, Lisa, what are your thoughts on Bitcoin as kind of abstract concept?
Yeah, totally. I mean, I think this is true. And I think like one thing about this that like, I think is like still not taught in like a lot of school level things is like this like revolutionized kind of the way that people did distributed computing. This like first paragraph, it seems really simple, but it was like an entirely like different, it's a entire break from the way people had been thinking about how to do distributed computing before this. Like the fact you can leave and come back and use this concept of something called like proof of work to figure out like what everyone else had decided is completely new and novel. And it's the first time that people tried it, and like frankly, like it's impressive that it like worked, right?
Yeah, exactly. Right. Like that's the thing that I found like so interesting about it too, is that like this is something that actually works, right? It's something where Satoshi released it, and like ever since he released it, it's basically been unchanged in terms of like the fundamental structure for it. Like there's been some changes in terms of like SegWit, and like we can go over some of that stuff maybe, but like this, he released it out and like it's been working. And you can like go back and you can see that it works. And it's not something where it's like every once in a while we have to be like changing it and updating it and all those kinds of things. If you do that, we can go over Stockworks and that sort of stuff if people are interested. But this thing like actually works. It is like a very pragmatic solution to this problem. And so you guys might be wondering, if you've never seen Bitcoin before, what's happening on the right side of my screen right now. So if we go over here, we can start kind of pointing things out and saying like, what do we notice about this stuff? So if we look at each of these messages, these are update tip, right? So this is like the new best is this is the chain tip, that height 2267. So that's block number 2267. What the version number is it? Is it what kind of work on it from? You can see this is from like 2009. Okay, this is from like 2009, and the progress toward where we are right now is that we have like barely gotten anywhere, but that's okay. So, like Bitcoin was launched at like the beginning of 2009. So the white paper comes out end of 2008. 2009 is when like the first Bitcoin client gets released by Satoshi. And in this REPL over here, I can post a link to it, is I put a couple different versions of Bitcoin. So there's Bitcoin Core as it exists today. That's in the Bitcoin folder. Bitcoin's written in C++, and they're always looking for open source contributors. So if you want to contribute to a fun open source project, Bitcoin's always the coolest. There's Satoshi's version, which this is the alpha release. This was what Satoshi released in 2009. I think it was like January 3rd, 2009 when he released this. And if you notice, it's bitcoin.exe. Like he originally wrote it in C++ as a Windows client. And so one of the first things that some open source contributors did when they came to the project was they rewrote it so that you could run it on Linux systems, right, which was pretty cool. And then there's also this kind of like just a piece of Bitcoin history is there's this pre-alpha version. And so when Satoshi was developing Bitcoin, he spent like a year and a half on it himself. This is like according to what he's told people. Like nobody really knows who he is. But during that time, he was asking other cryptographers and other people from like it's called the Cypherpunk mailing list for their opinions about things. And during that, this is when he initially started writing out the code. He wrote main and he wrote node. And so Bitcoin's like a distributed system with nodes that talk to each other. Yeah. And so this is like his first attempts to run through and like actually start implementing this stuff himself, which is I think pretty cool, right? So you can kind of like go through and see he's got like a lot of notes inside of here of like his thoughts at the time and like what he's trying to work with and some bugs that he's trying to work on, which is pretty cool. So yeah, so let's go back over here, right? So it's like distributed peer-to-peer electronic cash. Like how does that actually work? Right. So we go to the internet introduction. This kind of just gives some context of that. Like basically people are using credit cards now and credit cards don't give good privacy. So this is why he wants to do it. The thing that he identifies here as like the most important like part here is like making it a distributed system. Right. But if we go down here, so what is needed is an electronic payment system based on cryptographic proof instead of trust, allowing any two willing parties to transact directly with each other without the need for a trusted third party. Transactions that are completely computationally impractical to reverse would protect sellers from fraud. Routine escrow mechanisms could easily be implemented to protect buyers. In this paper, we propose a solution to the double spending problem using a peer-to-peer distributed timestamp server to generate computational proof of the chronological order of transactions. The system secure as long as honest nodes collectively control more CPU power than any other cooperating group of attackers. So nifty. Do you want to, as the first one, maybe start explaining what double spending is and see if we can illustrate some of this in Python? I think that
yeah, that makes sense. I think so. Like, I think the way that I like to kind of think about like double spending is the what do you call it? When you've got like, so like in money, like physical objects of money, right? If I have a $5 bill and I go and I like, how do you like double spend a $5 bill, right? We have to like go and make a copy of it. Well, how do you make a copy of a $5 bill? You find like a printer, right? And like make a copy and print it out and then take it to the store and give it to someone else. And now you've managed to spend $5. But like if someone like making a copy of a $5 bill that someone else will accept as real currency is really difficult, right? So making copies of, sorry, there's like construction here. Making copies of the stuff that you're trying to do. Let me move over as far away as I can from this. It's like, yeah, the construction's noisy. I'm sorry. But it's like the general idea. Okay, so like it's hard. The general idea in physical world double spend problem is that it's really difficult to make copies of objects that are physical, right? But like as soon as you take that like $5 bills and make it digital, so to speak. So now when you say like, okay, I've got like a picture of like a JPEG, for example, like how expensive is it to make a copy of a JPEG on a computer? It's really cheap, right? It's really easy. This is like something that you can do like really, really easily, right? So this has like been like, so the whole idea with like a double spend problem in a digital currency, right? So Satoshi's also talking about like electronic money, right? He's saying all electronic money up until this point in 2009 is like a bunch of big banks that like send each other messages that say, hey, so-and-so has a credit card and they want to spend $100 at Macy's or whatever. So like he's basically, okay, how do we like take this digital money and how do we make a system that like is really hard to like make a copy of it? So if I have like a thing that says I own $5 online, how can I prevent it from like someone else saying like, oh, I have $5 and I've spent it like at Macy's and at like, I don't know, boba tea, whatever, right? Because it's so easy to make copies of stuff digitally. So the way that he came up with how to fix this is like, we're going to write these transactions into a record of transactions such that there can only be one usage of each like $5 bill in the entire like blockchain, in the entire blockchain. So yeah, so it's like, okay, how do we build like these like transactions? Because I want to send $5 to Macy's, but make it such that the $5, the digital $5 that I send to Macy's, I can't also like make a copy of it and resend it somewhere else later and still have that make like a valid thing. So yeah, so the kind of like the work that he's trying to accomplish, right, is how do we make transactions in a way that like one transaction will like completely make the money that I used to have and then transact it away to someone else. How do I make it such that I can never like re-spend that money? So that's the double spend problem. Hopefully that was like not super long explanation.
Yeah, no, that makes a lot of sense. So I think before we try to do some Python stuff for it, we can just do it on Redshift and kind of demonstrate like what this might look like.
Yeah, that sounds good.
Cool. So let's start.
You're gonna try and double spend a transaction, Cody?
Yeah.
You can double spend a transaction, would you? Okay.
That's really hammered.
If you start Bitcoin running, will it run on the same? I think I'm on the same replit as you.
Yeah, I think so. You'll be able to hit Bitcoin CLI against the same one.
Okay.
in the same REPL as me. So let's
Thing.
see. So what we're going to do right now. So what I was doing previously was I was just starting Bitcoin on mainnet. And so mainnet is like the real Bitcoin, right? Where it's like the longest proof of work chain that's been worked on since Satoshi originally released the client. There's a bunch of test nets and stuff that you can play with. And so reg test is for regression testing. It's just a local one to this REPL that I'm going to start up, right? And so when you start it, I want to start, this is me like starting the Bitcoin daemon, so the Bitcoin process on reg test. And I want it to start in the background. So start it as a daemon. And then I have to set a fallback fee for purposes.
I think newer versions of Bitcoin Core, I don't think you have to set this anymore, but I could be wrong. Whatever, it's fine.
Plug it.
I think they find this at default.
So then you can use the Bitcoin CLI, which is the Bitcoin command line interface for talking to your different like Bitcoin nodes, right? So I'm going to talk to the reg test Bitcoin node that I just started. I'm going to say get blockchain info. Right. So if we look here, so I just started this chain and there's no blocks on it, right? So I'm starting with nothing. There's like nothing over here. I can control, instead of doing proof of work, we're going to have like proof of Cody did a command, which is going to be like Bitcoin CLI, reg test. One second. So I need to make a wallet first, right? So that I can receive coins. I promise it's going to start making sense as soon as we start putting these things together. So a wallet default. Say which one it is. Cool. So now I have a wallet, right? And we can see what coins do I have. I have no coins probably. Sweet. And then whenever you have questions about Bitcoin CLI, you can just pass it. Sorry, you can just pass in help command, and it'll tell you what you should do. So if we go over here, I want to mine, and I forgot what the mining command is because I haven't used reg test in a while. You remember what it is, Lisa?
To mine it, generate to address.
Yeah, generate to address. So for that, I have to get an address, and we can go over what those are later. But Bitcoin CLI get new address. So this is a Bitcoin address. I'm going to send the coins to address. So I'm going to generate 100 blocks that are going to pay out to this address, and Coinbase transactions. We'll go over that later. It's actually mentioned in the white paper, which I thought was interesting. But cool. So now if I do get blockchain info, Bitcoin CLI, get blockchain info. So you can see that there's 100 blocks, right, that I just generated. And these are the block hashes. We don't have to get into that right now. But so now we have a blockchain of 100 blocks. And every block creates 50 coins. And those 50 coins I've been spending to this address over here. So if I do, that's the one in my wallet, reg test, list unspent. Actually, okay.
You need to, if you could get balances instead of list unspent, should be, yeah, you're going to have to do one more to make it spendable.
Yeah. You have to make it one more. So once we get to kind of the end of the white paper, you'll kind of see why we have to do that. But yeah, so if I go here now, there we go. So this is a Bitcoin, right? Bitcoins.
Not just one Bitcoin, 50.
Yeah. Well, it depends. So we like overload the term Bitcoin, right? So this is like a coin, and this coin is worth 50. And the unit that we call it is also called Bitcoin. This is like a coin that is worth 50 Bitcoin.
Right. Yep.
This is like why Bitcoin is so confusing sometimes.
Yeah. So, right. Well, this is kind of like, I think maybe if you think of it more as like this like object, this like list unspent object is like the $5 bill. It's like the bill. and then the denomination of it is 50, right? So you can have like, the thing in Bitcoin, maybe this is like a decent way to think about it, is like there's your wallet is full of bills, and all of the bills have different denominations, and instead of like, because it's not issued by a central currency, because it's like done by people in a peer-to-peer way, each of the bills in your wallet can be of like any size, any amount. Yeah. So that's just like, that's just like, I think, a good way to think about it.
Yeah. Sorry, he's got a good picture of transactions inside of here. But there we go. Cool. Yeah. So in the white paper, the way that he describes this model that he's going to be using is that transactions have inputs and outputs. And so this is like a single coin over here, right? And so if I do another one like this, and then I do this, so you can see now I have two separate coins, just like Lisa was describing, where these are like $5 bills.
Yeah.
Right? These are like
They're both
50
50
Bitcoin bills, right? Yeah. And so these, I can use these as inputs for transactions, which will then have outputs, right? And the way that we're going to stop double spending is that whenever I use this as an input, it's going to be completely consumed. So now this thing is invalid. And then it's going to have outputs that come out of this. And those are the new valid ones, right? So even if I make copies of this one, because it's already been spent, we can't do that. And so an example of that would be if I get a new address. Here, I want to send some Bitcoin to that new address.
You just send to, okay. You just use send to address.
I
don't know.
Yeah, we can send raw transaction. No, send to address.
Send to address will just do it. Yeah.
It's going through and building the whole thing. Send to address.
This is the cheating way. Yeah.
10. That one.
10 goes at the end. Yeah. Put the address first, and then the amount you want to send. So you like send to address, how much amount goes at the end. Yeah. There you go.
Cool. Okay, so that's the hash of that one. So then let's get this transaction and kind of break it down and see what just happened here. Get transaction.
Cool.
Yeah, so if we go over here, so actually let's break down the whole transaction. You want to do that?
Yeah, it might be easier to do it if I'm not used to this view. If you run it again, but try putting true at run the same command, but add a true at the end. What does that do? Nope. Can you try get raw transaction instead of get transaction? I'm just like, there's like a certain format of JSON that I'm used to seeing that like get raw transaction. Will this work? Do we set up? It should work. I know it just needs the.
Yeah,
if you're gonna do that, you can just do decode raw transaction instead of get. Yeah.
There we
Cool.
go.
Yeah.
Let's go this over. Let's see what happened.
So we're spending one of the bills from our wallet, and we're making two new bills, basically. Ah.
Sorry, new file.
Cool. So this is the transaction we just made, right?
Yes. This was that transaction that I just sent. So if we go over here, I had two coins, this one and this one.
Yep.
And then I wanted to send 10 to this new guy right here. And this is the hash of this transaction. So if you want to walk through this one of how this works?
Yeah, we can walk through it. So there's like, we're going to take one of the bills that was in our wallet, right? One of the $50 bills, and we're going to put it inside a transaction and say, basically, we're going to be like, hey, I'm spending, you're telling everyone, hey, I'm spending this bill, right? That's in my wallet. And it's gonna be spent. We're gonna kind of everyone can forget that it exists. We're gonna throw it away because I'm spending it, right? It can't be spent again. And so the way that you do that is in the little transaction that you have. If you look over at line number 9 on the left side pane, right? It says VIN. It's kind of I don't know. I'm not gonna explain what that means right now. It's fine. But if you go down to this is basically a list of bills that you're spending. You'll notice that it's got a TX ID that you're spending, and it's got some other data in there. But I think that TX ID, that EA8B thing, if you go back to the list unspent, Cody, this is how you can map. This is how you can associate what was in your wallet, what bills were in your wallet, and what's being spent, right? So that one matches one of these two, right? Okay, so that's
the second one right here.
Yeah, exactly. So every bill in your wallet has a unique identifier, so to speak. And so when you spend a bill, you have to uniquely identify it in the new transaction. Yo, I'm spending this bill out of my wallet. And then you have to provide some proof that you have to provide some proof that that you have the right to spend that bill, because everyone knows about the bills. They're not secret data. So that's where these blobs of hex are. This is the proof that my wallet has the right to spend this bill, so to speak. Kind of I don't know, checks I feel are really old school these days. But if you've ever used a bank check where you write out what you're spending and then have to sign it, this data right here is basically the signing proof that's I have the right to spend money from this bill kind of thing. Yeah. Cool. Okay. So let's see where it went, right? So we had 50, right? We had 50. So if you look in the on the right, the left right side, it says we had 50 that we were spending for this bill, right? Amount is 50. Yeah, that one, exactly. So it says amount, there's no line number, but midway down, it says amount 50. Okay, so we're spending 50. We put one $50 bill in this transaction. So if you scroll down to the V out, so this is where we're gonna create new bills, right? We're gonna take that 50 and we're gonna split it into two. We're gonna split it into one of, if you look at the second one in here, the second new bill we're creating to put in someone's wallet, it's worth 10, right? And then and then we're getting some information in here, the script pub key thing, all that hex data. That's basically saying who has the right to spend it or what you would need to spend this bill. So include it in a transaction another time, is this on the top side. And then the one on the top is 39.999999947 something. That's basically us, because we the $50 bill we put in, we're only sending 10 of that 50 to our friend. So we want to send the rest of it back to ourselves, right? So once you use a bill, that $50 bill is gone forever, right? So you have to basically create a new bill that gets sent back to your wallet. And Bitcoin Core will do this automatically, right? We told it to send the 10 and it sent the 10, but it automatically sent the 39 and some change back to ourselves. So we actually call that the change output, right? That's the one that I had a $50 bill. I needed to send 10 to my friends. So I made a new $10 bill for them. And then I had to send the rest of it as change back to myself as a new bill, I think. Which is kind of weird. So bills are one-time use objects, right? And then once you put it in a transaction, you can't ever spend it again. You can't spend this so the fact that you can't spend it again is the reason why you have to create a new one with your change in it, right? Because otherwise you could just subtract the value from the existing one. But Bitcoin, once it's spent, it's gone forever. So
yeah, exactly. So, and this is in the white paper, it's a section 9 when he talks about this. This is the transaction model that we were just looking at, right? Of that we had this one, we had one input, which was this coin that we had right here.
Yeah.
And then we had two outputs, and one output was the payment, which was the $10 that we were sending to the other guy. And then this one was the change output back to ourselves. And you notice that the fee is not here. The fee is implied by the difference between these. We can go into how the fee goes to the miner later. But I think the more fun one right now, and what I've kind of got prepped for you, is because it's fun watching Nifty try to code these things live. Is the hash chains, right? So let's kind of move away. So this is how the transactions work, right? And so just for everybody who wants to play around with Bitcoin from inside a REPL, you just go through those processes. I'll put links to other tutorials that I've made for how to get started with them. But the basic idea is just you start Bitcoin on whatever network you want to be on. So you can start it on mainnet. The REPL's got some pretty limited storage though, and so you're not going to be able to store 500 gigabytes worth of blockchain data for that. You can start it on Signet, which is a signature net, which is like just a smaller chain that you can play with. That coins aren't worth anything. You can do it on testnet, or you can do it on RegTest, which is what we've been doing, where we just have this local blockchain that we can control. We don't have to rely on miners to do stuff, right? Because if I want to make new coins, let me just go back and do it. Yeah. So if I want to make new coins, then I can just make them myself right here. But the way I'm doing it is on the blockchain. Right? So there's a bunch of them. But okay, cool. So let's go over here. Let's go back to hash chains. So
hash chains.
Lisa, how do I know the order of these things? What if I try to spend those same coins like 3 or 4 times? What if I make multiple transactions? What if I go?
Yeah, right. So like, I mean, in theory, you just made a transaction, right? We were looking at one transaction and we are saying, oh, this villain's like one of the bills out of your wallet, right? And then no one can ever spend it again. We didn't explain how that happened. Like, you'd be like, yeah, okay, well, what if I just like make a new transaction and send it, like who's like enforcing the fact that I've already spent these coins, right? And the answer is we use consensus, specifically Nakamoto consensus, to make sure that everyone is currently at consensus. That means every like Bitcoin node on the network agrees what the current state of which coins like have and have not been spent. And this is like literally all that Bitcoin consensus is doing is like seeing or like making sure that everyone has the same view of what Bitcoin coins across everyone's wallets globally have not been spent yet. So as soon as a transaction gets spent, and this is where like getting a transaction into a block, like what is that actually good for? Like, why do people say like, oh, a Bitcoin transaction isn't valid until it's in a block? The answer is that until it's in a block, there's no guarantee that like that bill, like that coin or bills I've been calling them from your wallet that someone put into a transaction to send to you, they won't create a different transaction with that same bill until only one of those transactions can get into the blockchain. And so by waiting until the transaction is actually in the blockchain, you will that's how you know that you actually like get that money, so to speak. Okay, so the way that this happens is that like the blocks get like built on top of each other. And so you need to make sure that everyone has like the same view of which transactions have actually happened. So everyone needs to get like the set of transactions that are considered like to have happened on the network in the last 10 minutes at the same time. So in order to do this, Bitcoin uses this thing called a block. One way that I like thinking about blocks as they're like, it's kind of like batch processing for transactions, Bitcoin transactions, right? So the total number of possible transactions or possible coins that can be spent or whatever have to in like a certain amount of time on Bitcoin have to be able to fit into this batch. And so basically what the miners are doing is they're taking all these like proposed transactions and then they like, I don't know, they do some proof of work stuff. I'm going to hand wave over that. They're like doing some computation things in the background, which maybe we'll talk about. And then over a set of transactions. And then one of these is kind of like a lottery to see who figures out who gets to make like the next batch of transactions actually add to the chain. Once they get found, basically they, once that like, anyways, at one point, one miner somewhere is going to find like what we call the winning block hash. And again, handing wave over that. But like the official thing is that's basically like putting a seal or a stamp on that like batch of transactions, so that like every Bitcoin node on the network is going to get that new batch of transactions. And the hash that the miner computed is what's going to tell them like all of these transactions are good ones to consider as like being spent. So it's almost like you need like a seal of approval to get. So it's like, this is kind of like, I feel like maybe you can kind of think of it, and you're not trusting a miner. Like it's all proof of work. Like there's math, you can check that the miner did the right work. But when you're making a transaction on Bitcoin, you really kind of do need someone to like stamp off on it, and that stamp off on the transaction to make it like a real final transaction is a miner putting it in a block that they do work on top of your transaction, basically. Okay,
Yeah.
did I say it too much? Maybe that's like confusing.
No, I think and it's a good lead into some of these problems that I've got prepped for you. So,
Well,
yeah, so this is where I kind of wanted to go for us, right? Because like the
Okay.
innovation here with Bitcoin is like the solution to the double spending problem. The way that he solves it is by doing these hash chains with blocks, right? And so we can kind of
yeah.
explain a little bit about hash chains for these. But the stuff that we're going to code through real fast, and then after this we can go to Merkle proofs, which are super fun, right? But the stuff we're going to code through real fast. So let's just take this and move it into main real fast.
Yeah, so great. So you were talking about ordering, right? So there's a bunch
Yeah.
of like batches, right? And you need the batches to be in an order. So you have a bunch of transactions that happen. If the transactions aren't ordered though, that like doesn't help you with a double spend problem, right? Because you don't know like which coins got embedded before which. So how do you take these like series of batches and make it such that one has to come after the other, right? Like how do you prove like batches happen one at a time? How do you prove like a linearity between batches? And the way that they did that is so cool. It's actually like if you like this idea from Bitcoin, maybe this is like too much info, but this idea from Bitcoin actually comes from one of the footnotes in the Bitcoin white paper. It's actually one of my favorite. I think I haven't read all of the like papers in it, but this was like my favorite one of all the ones I did read. It talks about this thing called time chains. So basically Bitcoin like took this concept from another paper that was like came out with in the 90s about time chains. And the whole idea is like, how do you prove that the data that you've got now is built on data you knew about like 10 minutes ago, right? So how do you like order the order data in such a way that like if you know that like order batches, I should say of transactions. So you know if you're looking at like batch like number 10, you know for a fact that no matter what happened, batch 9 definitely had to like be known and made before batch 10 could be made, right? So how do you like order these batches is kind of the question we're trying to solve. Cody, do you want to explain, or like I can explain?
Yeah, well, let's just start writing code for it, right? To kind of walk
Great.
through it, because like we've got hash lib, right? So
We got
that's,
hash lib. That's all you
yeah,
need, right? All you
this
need
is
to
the way
replan
I think
Bitcoin
to do
Core
it.
is a
So
hash lib.
let's kind of go through, and this is like why hashes solve this problem, right? So
Hashes.
move this stuff out of here, right? So we're going to use we use cryptographic hashes, right? So basically the idea behind a cryptographic hash, if you guys have never heard of these before, is that for you just want something, it's kind of like a blender, right? So it's like I take like an orange, an apple, and a banana, and I drop it in the blender, and then I get a smoothie out, right? And like you can't unblend the smoothie. It's like once I have the smoothie, you can't go backwards. So just showing you what the smoothie is, I can't tell you, you can't like from the smoothie know what the fruit were, right? But if I
Right.
tell you the fruit, you put them in the blender, it goes through, then you see the smoothie, right?
You get
And
the
so,
same smoothie out every time, right? You follow the same recipe.
yeah. So
Um,
if we do this one, right? So I'll do like import. I just want to
Hash
do
lib.
this in the REPL. So let's do I don't know, like bytes of Cody is demoing cryptographic hashes. Okay, so this is going to be our input.
Note that little b at the front is very important in Python for this to work correctly.
Yeah.
Just FYI.
So that's saying like the byte encoding of this.
Of this string, ASCII string.
So let's do hashlib.sha256 of this is going to be like our blender, right? This is the hash function that we're using, is of that input.
Will it blend? Will it blend? I don't know.
What is it? It's a.
Do you want hex digest or do you want digest? Do you want like yeah. Boom.
Cool. All right. So basically, you can take any input, encode it as bytes, drop it in the blender, and it'll do a unique output like this, right? And so if I modify, let's do different input. So if I modify this and use something else, right?
Why don't you make it almost the same except like off by one letter, maybe?
Yeah. Cody is MOing. That's a B instead of a D, right? Cryptographic hashes.
And then do the same thing on a different input. All right, so wait, before we, okay, so how different do we think the output's going to be, right? Is it going to be 1 letter off in the output? Is it going to be 10 letters off in the output? Looks like it is like every letter is different, right?
Yeah, so it's completely random, right? And so basically, if you don't know what this one is exactly, it's not like an optimization problem where you get closer and closer as you're trying to find it. Is every guess is as good as every random guess, and there is no way that I can try to find this except by just trying random things, right? And so
the search space is really big.
Yeah, I would start with A, right? And then I would do that, and I'm like, oh, I didn't find it. Okay, now I'll do B.
It's a mystery smoothie, right? Like if someone gives you a hash and they're like, man, this hash is like really tasty for a smoothie. Like, what's your secret ingredient that you put in it? Like, you know, they like have no idea. You're like, I don't know why this is so good. Like, it's really good, but I don't know why.
So if I take the outputs of these hashes and use them for different hash, like as inputs to new hashes, right? So I say
hash
like the output of this one becomes the input to my next one, right? So I'll do like, I don't know, 4I in range 3.
Are you just gonna hash maybe I?
Hash lib dot 256 into bytes, right? It's just I dot bytes or 2 bytes.
Yeah, I think that'll work. I to bytes, except you're gonna make it 1 byte and it's gonna need to be big. So
that's okay. We'll try that.
I don't think that's gonna work.
No, because I have to feed I back into itself. Sorry, I can't use a for loop here. So let's do like I equals. Let's do this bytes of hello, and then we do counter equals 5, right? And then we do I don't know. Well, counter greater than 0. This is not clean, but it's okay. Let's do.
So the general idea is we're gonna start with this initial thing, byte thing of hello, right? And then we're gonna take the hash. We're gonna take hello one time. We're gonna hash it. That's gonna give us a result. And then we're gonna take the result of the hash of hello, and we're gonna maybe add some new data to it, but pass it back into the hash function, and we're gonna get a completely new like hash output, right? So this is kind of like chaining hashes together. So as as this while loop that Cody has made counts downward, so to speak, we're gonna make like 1 hash for every round. But the key point here is that each hash round that you make is going to contain inside of it as an input to the hash function. So that means like you needed to know it before you ran the hash function. The result of the hash from the previous round. So basically, if you wanted to like recreate the final hash that we're going to get out of this, you would need to have known, or you would need to know the original input data, and then all of the incremental data that maybe we added along the way at each of those hash rounds, in order to like recalculate the exact thing. What's really cool about this is that like, I don't know about you, but I always think just like first time I heard about this, it sounds really complicated. Like, what do you mean you're chaining hashes together? That sounds difficult. But the key thing to think about is like a hash function requires you to know some data that you put into it, right? So as long as you know what the inputs to the hash function are, you will always get the same result. This is called being deterministic. If you put the exact same information in, you will get the exact same result out every time. So it's repeatable. So what's cool is that I can like give you kind of all the parts to like the hash function that I've like created, or to the hash result that I've gotten. And in our case, it's gonna be okay. Take the word hello as bytes, so the be hello, and then hash it 5 times. And when you get to the end, like that result is gonna be, whatever hash you get. And if you wanted to recreate that hash, you could verify it. All you would need to know is like, here's the hello data, and then the instructions of how many times to hash it, like 5 times, right? Is that useful, Cody?
Yes, that is very useful. Thank you.
Oh, you're writing a function. Okay, cool. I was
Yeah.
like following along with it.
Okay. So
where are you writing that thing? I'm just gonna like try and find it. Oh, you're in my main. Okay, gotcha.
yeah, I'm just in main. So let's see if this one works. Okay.
Cool.
Okay.
Do you want to take 2 seconds to talk about how cool Replit multiplayer is? So like,
oh yeah,
we're like streaming, like, yeah. So it's really cool. So the reason I was like, I don't know where Cody is. I found him really fast because multiplayer is really dope. It's got like, it's got the ability to see where other people is. But basically, like, I'm looking at a Replit on my laptop I just have it open, and Cody and I are basically like sharing a Replit, so I can see everything that he types, he can see everything that I type. It's a really great way to like pair with someone like wherever they are in the world. So that's pretty cool.
Yeah. So this is like how we're going to start hash chaining, right? So if you can see here is that I'm going to be printing, this is like the counter. So this is like where I'm starting at. And then this is like the hex. This is a hex encoding. That guy's really loud.
Is it? I can like turn my thing off. I know. I'm sorry. It's like, here, let me mute myself.
So these are the bytes at this point, right? And then what we're going to do is we're going to take a hash of those bytes and set that to I, right? So the hash of hello is this thing. The hash of hello is this thing, right? And so this is like the point of hash chaining, right? Is that the only way that I could have arrived at this number is if I knew what the input was. And the input was this thing. And the only way I could have arrived at that number is if I knew what the input was over here. And the only way I could have known what that number was if I knew what the input was over here. And so when you have these long chains of hashes, whatever the most recent hash is must have occurred after the earlier hashes, right? So let's say that in here or whatever, I want to like, instead of this being hello, this is like Cody pays Lisa $10, whatever, right? So when I get this, everybody agrees that like at this point in the chain, at this point of the blockchain, that this is what the hash is. So let's say I try to go back and I try to say, hey, actually, or Lisa tries to go back and says like, hey, Cody stole another $5. He tries to change this transaction so that it's Cody pays Lisa $15, right? Well, now I changed this input, which changed the hash, which changed the hash, which changed the hash, which changed the hash, right? And so this is just, it takes like, half a second or whatever when we're doing this. But what if we added like a difficulty to this? What if we said not just any hash or whatever, but in order for this thing to be valid, it has to have like a certain number of zeros at the beginning.
Yep.
So let's kind of start that, right? So how should we do this? Let's do this one. Okay. So let's set difficulty. Difficulty is, let's call it 5, right? And so I'm only going to accept as a valid hash something over here if it's got a certain number of zeros or whatever, right? And so you can go over here and let's just, as an arbitrary rule, anything after the period, you can do whatever you want with, okay?
Mm-hmm.
So over here, in order for this to be like a valid thing, in order for this to be a valid next block or whatever, the hash is going to have to be below that 0.0000000 or whatever, right? Actually, we don't have to change too much when we're doing this, right? It's just over here. It's just okay.
Right. And so one way to think about this that I find useful is like, so I think there's 2 things here that are like kind of useful. The first thing is those big hash values that we're getting, like every time you run hashlib and then print it out, it gives you this long garbled string of hex, right? that's actually a number. You can take that and you can like convert it to like an actual like number, or maybe it's a better way to think of it as like bits, right? So like how many of the first bits at the beginning of this like long string are zeros, right? Maybe that's a good way to say it. I think that works. And so like basically like if you think about like, so a hash function, as Cody was pointing out earlier, and this is cryptographic hash functions, like a hash function, it has to basically be cryptographic for this to be true about it. I think I'm gonna hand wave over that. It's like slightly true. There's a couple properties of cryptographic hash functions. This is one of them, I think. And that's it, like the given any random input, the output that you get should be evenly distributed across the entire range of like possible output values, right? So like, what's that saying? Okay, so like let's say that I was using a hash function, they put out like 8 bytes of data, for example. What is 8? Let's say 8 bits. Let's say that it's a hash function that like hashes things to 8 bits, which is like 1 byte. That means that there's like how many different like combinations of 8 bits are there? There's like 256, right? Because that's 2 to the 8. So that means that if I put anything into this like magic hash function that I've come up with, and I put 256 things in there, I would assume that like every time I hit it, I would get like my chance of getting any one of the numbers from 0 to 255 starts at 0 would be equal no matter what I put in there, right? So every time it's like running a hash function is kind of like rolling the dice, right? Except the size of the dice is like for these like, what is it? 256 is 256 bits. There's like 256 bits that you're like rolling the dice on, so to speak. So each of those is going to be like at a different value, but it should be randomly done for each of the 256 bits. So you're basically like doing like a dice roll with like 256 one value, like 2 value dice, either 0 or 1. And you do that every single time that you like calculate a new hash, except that like if you put the same input in, you'll get the exact same dice roll out, so to speak. Why am I saying this? Okay, why does this matter? So whenever you say, okay, like there's 256 bits, when you roll all 256 like 2 value dice, like it's either going to come up 0 or 1, there's like the 8 bits at the front, let's say, have to be 0, right? So then you can start using like probability or math to figure out how many times am I going to have to roll the dice on average before I'm going to find like a roll of all those dice where the first 8 in a row are 0, right? So that becomes like a probability game, right? I don't know how to calculate it. What's like 8 out of 256? 8 out of 256 is
0.03.
0.03. So I don't know. Wait, what does this mean? I need to get 8 roll. I'm so bad at probability, but this is like really important for understanding exactly like being able to calculate. But like, I guess the question is like, if I need 8 zeros in a row, how many times am I going to have to roll the dice before? Like, let's just imagine I just had 8, because I think 8 dice is basically the same, right? Is like 8, the first 8 out of 256. I think you'd have to, how many times do I have to roll 8 dice before I would expect all 8 of them to be 0 if the only 2 values you can have are 0 or 1? I think it's a lot. I think it's too. I think it's like, I think you need like 8. So you need like half the time on the first one, 50% of the time on the second one. So I think it's like 0.5 to the 8th or whatever is like what that ends up being. So 1 over 256, which is 0.0039 is what I get. So basically you would expect to need to roll almost 1,000 times. You get 3 out of every 1,000 rolls. You would get you would expect the first 8 bits to be 0, right? I think that's right. So basically that means you need to like oh, you just stopped sharing your screen, Cody. I don't know if you did that.
Sorry, I'm fixing it real fast.
No, it's cool. But like so like this is like, okay, so this is kind of where the 8 out of 256. It's actually like it's actually gonna be, I was wrong. It's 1/2. It's gonna be 1/2 to the 8th, right? Because I need 8 at the front. So like if you think about it, so like just like 8 dice, right? And each of the dice again only has 2 sides. I know I keep saying that. I guess it's like coin flips, but I like thinking of them dice. Whatever, it's fine. But each of them can only be 0 or 1, right? So there's a 50-50 chance on each one that you'll get 0, and there's a 50-50 chance 8 times. So you like do that to half times itself 8 times, which is raising it to the power. So that's this much. This is how often you would expect to get 8 zeros in a row.
Yeah.
Yeah. But then like Bitcoin makes it a lot. Like I don't actually know how many we're up to right now, but I guess if it's like, I don't know, let's guess it's like 56.
Well, that's what I want to jump into, Lisa. So that's why I kind of moved over this because we're kind of running low on time, but I want to get through this stuff. So this one, what we're going to be doing here is getting Bitcoin block header data from Explora and verifying the integrity of its hashes.
Hell yes. That's
So
cool.
this is like a fun one, right? And so this is exactly what Lisa's talking about. And so we're going to see when we go through this of like what it is. So Lisa, do you want to take this first one?
Yeah, let's go.
Okay,
look at all the zeros on that ID though. That's what we're talking about. I got all the zeros at the front, right?
Yeah, so this is actually super low, right? So this is blocks 100 to 91, right? That this one was. This was my
example. But what's cool about these zeros though is every 2 zeros represents those 8 bits we were talking about, which was this number that's like the 1/2 over 8 thing, right? So there's this many. You had to roll on expectation like over almost 1,000 times to get every 2 pairs of zeros on this. So this is like a lot of rolls of the dice. Is all I'm saying. To get like find this number. Okay, cool. So basically the way this works is like, how does a block header? A block header is a it's like a set of data. It's got like a ID, which is the hash of all the data inside of it. It's got a height, which is like not included. That's sort of like some extra data you can calculate if you've been counting blocks. But the version it's going to contain a timestamp. It's going to take a transaction count, maybe. Yeah, it should have a transaction count. It's not going to have a size and weight, I think. It's going to include a Merkle root, and it's going to include the previous block hash, and definitely has a nonce, and maybe the difficulty bits. I'm not sure. Okay. Okay, here we go.
It has bits.
So all that's going to go into this. So like what we're doing is we're building a hash. Like we're building the data, I should say. This is like the apple, the orange, and like the, I don't know, the special coconut flavoring we're going to add into our smoothie, right? So what are the parts we're putting in our smoothie? It's going to be the version, the hash, the Merkle root, the time, the bits value, and the nonce. And then you can see how we're going to, like, just how I said it, we're going to add these all together. It's like apple, orange, coconut to the pre-image. And then once we have the pre-image, I'm gonna just go ahead and start filling some stuff in here. Oh no. Why is this broken? It's fine. We're gonna do the SHA-256 of the pre-image.
Oh, hey, you're all the way down here. No, I was starting at the top.
Oh, starting at the top. Yo, okay.
Yeah, so this is the first one. So let's yeah, so up here. So we're gonna get 10 Bitcoin blocks from Blockstream. So if you guys want to use Explora, it's like an API that Blockstream maintains for getting Bitcoin data. So this is like the Bitcoin blockchain, right? Like the main chain Bitcoin blockchain. This is like there's currently 778,826 blocks. And if you want to get data about it, then you can use the Explora API, which is what they maintain over here. So that's what we're going to do in this REPL, is that we're going to use blockstream.info, which is Explora, the API. And I want to say, hey, get blocks starting at this block height, right? And so if I just go down here and then out for a second, run it. Should work. That's because
you double in. I got you. I think you're good now.
Invalid URL.
Invalid URL. No schema is applied. You got to put the HTTPS at the front. Yeah. No schema.
Because I need to turn this into text.
Cool. Dope. Well, that's a lot of data. Oh my god.
All right. That's a lot of data. So
entered the matrix. What's going on here? No, okay.
So we can work on formatting this, right? But it's getting the data at least now, right?
Yeah, that's definitely getting some data. I don't know.
Because I think I'm double dumping it, is I don't need to do that. Is that I just need to print block. There's like a lot of data.
Yeah, maybe next time we just pull a piece out of the block headers. I don't think you're getting like the block header. You're getting like the whole block. That's like all the data. That's like all the transactions in 100 blocks. That's like 200 megabytes of data.
All right. Yeah, sorry, I hit the wrong endpoint. We go over here, East Flora API. I want to get blocks. Let me just make sure I got this right. Get block about a block. I want to get the last 10 blocks.
You want to get block headers, right? I don't actually know. Where are you looking to look at the API thing?
Mempool.
Oh, the mempool.space stuff. Okay.
Blocks. That's what I have to do. Is just do block. Let's see what that returns. Adapting on the fly. There's console. Dex invalid hex string. Sorry, let me just see what I'm getting when I return this. Invalid hex string.
Where are we? That's on line 26. Line assert len equal. There's nothing in len, I think.
Oh, okay, gotcha.
Yeah.
Sorry, can we just comment this stuff out and then
fancy.
We have 10 blocks. Invalid hex string. Why is it throwing that?
Probably the print is printing out the text that it gets from the thing.
Yes.
So
400. Oh.
400 is not a valid
Yes, that's
API response. Oh, maybe the block height thing that you're passing in was invalid hex string. So what we're reading was the error message the API was sending us. So that's
it's because I'm using an F string here. That's
200
why.
is correct. Yeah, 200 is right. So now you should be able to get the text out. So if you do like .text now, it should work.
Yeah. Okay.
This is gonna give you a bunch of data again. Oh, okay, maybe not. Just kidding. Hey,
yeah, that's what I wanted. Right.
Cool.
So yeah, here we go. So it's giving me those blocks. I don't know why I was doing that last time. That's okay. So let's go over here.
Extremely noisy here. I'm gonna mute myself for a little bit.
Okay, that's all good. So if I go over here, I'm trying to get block headers. So JSON.dumps. Should be nice. It's doing it as a list. Because it's doing it as a list right there. I want to unbundle that list. If that it's text right there. So I think I have to load that in a JSON. Sorry. Is that box equals JSON? Call this one blocks. On the fly, which is fun. All right. Well, it's printing it as a list, which I don't want. I want to print it as separated out. Oh, dumps. I don't know. Why is it not doing that? Oh, there we go. Okay, because I'm double printing them. All right, sweet. So, there we go. So here we go. This gives me the last 10 blocks. Okay, that was an adventure, but that's okay. So this gives me the last 10 blocks, right? So I want the block, this is the blocks from height 100 all the way back to 91, right? And so each one of these, as we can see, has like the, you know, it's got the ID, it's got the height, it's got the version, timestamp, transaction count, like all those stuff, right? So if we go over here, this block 100 over here, I think it matches, right? Yeah, so this is the same one. So let's go uncomment these tests. And this one should pass. So if I do that, cert len. Yeah, so here I'm just testing to see if this works, right? So it's like I want to get the 10 previous blocks from whatever I pass in over here. And I know that block 100 looks like this, right? So I'm going to be comparing to see whether or not block 100 matches the one that I have over here, which it should. That object of type none type has no len. Because I'm not doing this right. Because I'm not returning here. There we go. Okay. So that should work now. Cert. Yes, it does. Which means it'll pass this. Yes. Okay. All right. So brief detour, but we figured it out. So over here, this is get 10 previous blocks. And so it's getting the 10 previous blocks. And so it's just not pretty printing them right now, right? This is testing to see that the block 100 matches. So then let's go over here. Now we're going to verify that these blocks match what they're supposed to. So every block should, if we go over here and look at this one, there should be a prev hash inside of here. Previous block hash, right? So this is the previous block hash that's embedded in 100. And so this previous block hash should match 99's hash, right? And so those are the functions that we're going to run right now, which is good. Sorry, that took a little while. Let's debug that live. So helper functions over here. We're going to use SHA-256D. So return. Let's say the data that we're going to be passing in is a, yeah, let's have it be bytes. So return hash lib 56. 56 data. Yes. The reason why is because Bitcoin block headers are hashed twice instead of once. It's just like a thing that Satoshi did. The reason why you want to do that is the reason why he thought he was doing it was because to prevent something called a length extension attack, but that actually doesn't apply here because it's a you just imported SHA-2. You imported SHA-256. Thanks, MP. Okay, so flip endianness. This is another thing is that you have to flip the byte order, and the reason why is because the computer that Satoshi was using when he did this was it was an Intel chip, and so when you're using an Intel processor, the bytes that are encoded in when you're compiling with these stuff or whatever is in instead of reading it like just normal left to right, whatever, you actually read it 2 at a time backwards, right? And so you'd read this one as like 9519 4B 8567, right? And so you have to have these flip endianness functions that does this. So let's assume that we're passing in bytes here. And so if we're passing in bytes, use list comprehension to flip those. Okay, format block header. We have to format this. So when we get these back, we have to take all of the inputs that we need for these ones and then like concatenate them together and then hash that thing, right? And so that's actually kind of complicated, but so we might not get to that right now. I've got the answers for that, so we could do that later. So then over here, verify Bitcoin block takes two sequential block headers, block and previous block, verifies that block builds on the first block. Return true if the previous block hash field in block matches the SHA-256 output of the previous block. So if we go over here, this will do it, right? So yeah. So this one, previous hash would be equal to when we pass in yeah. So write a function. I forgot how I did this. So concatenate all the fields together in exactly this order. Oh, there we go. That's how I have the instructions right here. So this one works. Then find the SHA-256 output as hex digest and verify. Well, I like wrote most of this already.
Do we need to flip the Indianness on the Merkle root, or is it fine?
I don't think we do. We can test it, but yeah. And find the SHA-256 output as hex digest. So
previous hash equals block.
SHA-256D. Image. I think we're gonna have to convert these to bytes before we pass them in. That's okay.
Are they not already? Okay. These are gonna need to be bytes before we flip them.
Yeah. Or you can, in flip Indianness, you can convert it to bytes. That might be fair. But let's find the show. Fix me. Okay. If block.
Wait, this isn't right. This is data is already as an int, so I just need to convert the int to a bytes, and then hang on.
Yes.
Wait a second. This is. It's not from hex. It's int's 2 byte.
Yes.
2 byte. 2 bytes. Does that work? I thought you should be like 8 and like we just do this instead of flipping the Indianness. I don't know. Be lazy. I don't need that. I do need that. No, it's not 8 bytes. It's only 4 bytes. JK.
Yes.
So I'm guessing version, time, bits, and knots are all going to be exact same.
Probably.
Why does this not work out quick too? It's fine.
Here, let me just go over here. Do we call format block header anymore? No, we don't. That's fine. So we actually don't need this one.
What was it? Median time.
Format block header. Blocks. Blocks plus 1. Okay. Yeah, I kind of forgot how I did this for a second. So over here, let's this right.
I think that works. So the big question is previous black hash and the Merkle root flipped or not? I don't think they are. Oh, actually, I need to convert these to bytes. These need to be
Yeah.
bytes for real.
Yeah. So all these ones are bytes, and you concatenate them all together. And then you take the SHA-256 of the pre-image, and then you do that. Yeah. Okay, that works.
This is going to return a digest, though, so I think you're just going to want hacks here.
Yeah.
Okay.
Okay. Cool. All right. And so for this, we actually don't need format block header at all. Right?
Well, I think we did format block header right here. This is actually, we could just like pull this if we wanted to. This would be the format block header part. Maybe we should do that. I'm just gonna pull it out here, I think, and put it here. I don't know what block is though. Oh, this is the wrong thing. Hang on.
Yeah. So this gets to block and previous block are going to be that it gets this block and this block, right? And then it passes in like block 100 and block 99. And then it's verifying that block 99, when you get those fields off and hash them, equals blocks. There we go. Yeah.
And then the preimage is going to be equal to, why are my preimage is going to be equal to the format block header of the pre-block, right?
Yep.
Yeah, that should work.
Yes.
Maybe. We'll see.
Yes. Okay. Let's give that a try. So we go over here and get rid of the prints.
Well, no, like, yeah, I'm not sure about this pre-patch thing. That's fine.
That should probably work. I don't know. We can debug it. We still got like a couple minutes. So assert blocks. Okay, so there we go. That's why these ones are not matching right now. So
here, I'm just gonna add a print here.
Yeah, let's print right there.
Oh wait, is it doing what I think it's doing? Yeah, okay, that's cool. It's black hash. I could be lazy and just try one thing and see if that fixes it. We can just try reversing these.
Which one? Oh yeah, no, we didn't call flip ending this for those.
Yeah.
That'll do it. Yeah, so this is we're getting to it.
Will that work now? Does it work now? Did I just fix it? Maybe I fix it.
Assertion error. Okay, we're slightly off, right? And so this is kind of getting back to like the hashing, right? Of that, we know that to find this takes a lot of work, right? But to find this hash over here does not take any work, right? This is like basically just looks like a random hash, right? And so this is the correct hash. And so we know that if we get everything in order and we get everything right, then these two hashes are going to match, right? And you can't falsify that. Okay. Oh, wait. Hey, that was actually really close. You just have to flip the endingness on the back of it. Please.
On which one?
Yeah. On the return, you just have to flip the endingness.
Where's the return? Oh, here.
Yeah, the output.
We should probably do that before we return it, just because, right? Those are the same. No, they're not. They're very close. Why are those like really close except not?
Wait, they're double flipped. Because I did it as a hex. That's why. Is this okay? There we go.
I think you got some stuff there. There you go. Yeah.
Yeah.
Does that work? Oh, dope.
Yeah. Okay. Cool. So that all right. So we went through stuff really fast there, right? But this was actually pretty cool what we just did. So the stuff on the left-hand side over here, this is like the this is like the block hash, right? Because this is for each block. Well, let's just add prints for this, right? So that we can actually see what it's saying there. So where's the prints that we're doing? Doing this one. we'll call this like block block data. So we'll call it block data, whatever.
That'll work. Oh, okay.
Calculated. It's kind of done well, but that's okay. So if we just run this real fast, it should work. Right? Okay. So if we look at this, so what we kind of just walked through here is that this is us calculating the block hash. And this is block 100. And this is the hash. So this is in block 100. It says, hey, I'm building off a previous block, which when hashed produces this number. And this one over here is block 99's hash. So we can say like this block builds off of the block that hashes to this thing. In block 99, it says, hey, I'm building off a block that is built off of this one. And so we say, okay, well, block 98, when I hash it, it goes like that. So let's I should clean this up a little bit just to make it so it's easier to see. So block, let's go here. So we can print in this one, right? So we can do like print block height. This will be like block. Okay. Block height. There we go. For block height, there. Prev hash. No, it's okay. You don't have to do this. Kind of makes a point. That's fine. But so, yeah, for like each block, it's like, hey, I'm built off a block that when hashed produces this number. This is the previous block that when hashed produces that number. It has a previous hash in it that says when I'm hashed, I produce this number. Its previous block when hashed produces that same number. Because they match, we can say like this one builds on this one, 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 right? Which is pretty cool. Okay. Yeah, there's like a lot of stuff that I thought we were going to get to that we didn't get to. That's okay.
It's a pretty normal day in the life of a developer. Okay. Yeah. Okay. Cool. So I mean, it sounds like then we've got more to do in next week, maybe.
Yeah, maybe I'll plan another one. Yeah, but just so this, I'll share the REPL that I'm doing this in. So I've got some other stuff in here, right? So I've got like this proof of work blockchain that I built, which is like it makes a blockchain and it makes a block and it's got miners and like they like mine and try to like find a block, which is pretty fun.
That's fine.
And then I've got this SPV Merkle proof that I wrote yesterday, which I was really proud of. This one is that so if we take, let me just copy this over so we don't lose this. We go over here in the white paper. It covers something called Merkle proofs and how you can use them in order to verify the integrity of the block. So like this is just the block headers, right? So if we go back to the tutorial here, right? So the hash chain is done on the headers, right? So you take the block's metadata and then you take that, that's what we just went through. And then that gets hashed and that gets input as like the previous hash over here, right? So where is it? It's he's got another picture. There we go, right? So this is the part that we did right now, where it's like, hey, this block says that it has a previous hash. If I take the hash of this block, it goes into here. Instead of like actually doing all the transactions, you like Merkleize the transactions. You create something called the Merkle tree, and it looks like this, right? So you like line up all the transactions along here. You like hash them all together, and you make a root hash. And this block header thing that we just went through the hashing of, like that's the thing that gets hashed. So you don't have to do all of these transactions. So the block header is like, where is this? It's 80 bytes, right? But the full block can be like 4 megabytes, right? After SegWit, right? But so if we go over here, you can basically prove the inclusion of a transaction doing something called the Merkle root. And I wrote this thing, which you guys can play
It's
with.
a proof of inclusion, I think. Oh, that's cool. Proof of
Yeah.
inclusion, I feel like is the
We can go find a transaction. Yeah.
so good.
So if we go over here and find like a random transaction.
Oh, this is cool. So you can input stuff. Oh, this is nice.
So you input
Let's make a nice input text.
transaction ID and you hit enter.
Whoa.
And then it gets the Merkle proof. It builds the Merkle tree for that proof, right? And then it's oh, wait, sorry, my Bitcoin D is not running. That's okay. And then basically this hits against your Bitcoin node and then says like, actually I can demo that real fast right now. Is that you start the Bitcoin node in the REPL. Bitcoin D dash. So we're gonna have to get an early transaction in order to do this. Let's do 1, 2, 3, 4, 5, 6. Earlier. Okay, never mind. 1, 2, 3, 4, 5, 6. For some transactions. Right, so you get a transaction. This one. And then you pass it in. So what height are we at? Oh, we're really early. Okay, well, I can get anything up to. See, I want to show this because it's super cool. Is that basically does the proof against your local node. But so all of these transactions just have like 1 per, which is kind of annoying, right? But I could run it against my local, but I don't want to do that right now. It's actually going really fast. So let's go. It's going to take like 2 minutes in order for this to get up to a point where I could actually do the proof, right? But that's okay. That's maybe.
What time is it? Could I need to hop off in like 5 minutes? Just FYI.
Yeah. So I'll just get this one and then, but the Merkle proof for this one is it's literally just the transaction, right? So let's see if this works just with this one. Is that if I go here and hit enter, block height is out of range.
Oh, because you're using Regtest, right?
I am using Regtest. Wait, no, because I just started on mainnet.
Oh, you did? Okay, sorry.
Yeah, sorry. So
block height is at 2,500. What block height are you at? Did you get this out of your Bitcoin Core node?
This one. Copy, paste. Here, run it again.
Yep.
Okay, well, so there's like no Merkle proof to do, right? Because there's just the one transaction. Right? That's okay. Is that it works really well for the what's it called? It does it really well for the other ones, but that's fine. So you guys can play around with that. But okay, hey, thanks everybody. Sorry about the late start for that one. It's just a YouTube issue, but okay. Thanks everyone. This was fun. Cool. All right, end broadcast.